So we want to take our newfound projection of u onto v and its corresponding scalar into a real-life context, which will mean physics, of course. So we have a 100-pound block resting on an inclined plane that is tilted at an angle of 20 degrees to the horizontal. All right, so that means that this angle right here is 20 degrees, right there. Right, it has to be. Okay, lovely. So then we know that the block itself has a weight of 100 pounds. Right, so that represents the force. So the vertical vector W represents the force weight exerted by the object, and it can be decomposed into two pieces. You have the weight that is perpendicular to the plane, and then you have the weight that is parallel to the plane. All right, and our job is to find those two pieces. Find the part that is parallel to the plane and the part that is perpendicular. So the parallel component is going to be right here, and the perpendicular component will be I'm going to use hot pink. Will be right here. There we go. All right, and then just for fun, we can kind of put in the x-axis, because if I make that dot the origin, right there, that's the origin, where the block kind of meets the center of the block, if you will, meets the plane, then this is the x-axis, and this is the y-axis. And so the weight vector is actually the downward y-axis. I'm just kind of sketching it in there. It doesn't have to be perfect. All right, and then that point right there is the origin, right, that dot. Well, if you look at the bottom of the plane and the x-axis, they're parallel. And they're parallel and they're crossed by a transverse right here with that. So that means that that angle right there is also 20 degrees. It has to be. Okay, lovely. But that would also mean, if we think about this in terms of right triangles, that means that this angle right here is 70, because that would form a right angle with the x-axis, which means that this angle over here is also 20, because that also forms a right axis, or a right angle, because that's perpendicular and parallel, so that's forming a 90 degrees. So if this is 70 in the middle, then that's 20 and that's 20, because this is 90 right here, but then so is this right there. So you have two 90-degree angles. Lovely. We also know that the weight vector, the downward weight vector, has a magnitude of 100. So I'll just put that in there, right? Because the weight of the block is 100 pounds. Okay, so we need to figure out some things. I think it'll help if we kind of draw our triangle, or our parallelogram, if you will, in a slightly different format. So let me kind of draw this right here. So I see a triangle forming with this vector. Because vectors are free, I can put it down here just as easily as up there. That's another reason why this is 20 degrees. So let me redraw that picture, that triangle, just kind of the best I can. So that's my W perpendicular. I'm going to call it, I don't know, Y, just because I feel like it. And then the angle inside is 20, and then I know that my weight, which is going straight down, well, it's moderately straight, and that's my weight vector, and I know that side is 100. I know this angle right here is 20 degrees, and then I have the parallel vector right here. I'm going to call that x. Okay, what do I know? Well, I know that the sine of 20 is x over 100, and the cosine of 20 is y over 100. And I can use that to find x and y. So let me do that real quickly. So the sine of 20 degrees equals opposite, which is x, divided by the hypotenuse, which is 100. That would mean that x is equal to 100 times the sine of 20. And of course we could find a decimal approximation, but it's not necessary at this stage. Furthermore, I know that the cosine of 20 degrees is equal to y divided by 100. Therefore, I know that y is equal to 100 times the cosine of 20 degrees. right? Multiplying both sides by 100. All right, so I can use these pieces as needed to find my components, because that's sort of what I'm getting at. All right, now how do I find the vector? Okay, well, let's start with the parallel vector. So the W parallel portion, PAR for parallel, is the length of the projection times the direction, right? Like that. Okay, so the length of the projection is x right here, right? It's the projection, if you will, of the weight vector back onto the parallel portion, right? So if I drew a line straight up, that would be that projection. So that would be x, right? So this is x, but we just discovered x is equal to 100 sine of 20 degrees. So I'm going to put 100 sine of 20 right in there. That's my x. Okay, now what about direction? Well, okay, if this is the x-axis right here, my direction would be my unit vector going that way, which would be, this would be negative 20 degrees then for that angle. So my direction would be the cosine of negative 20 degrees times the sine, or not times, sorry, comma, the sine of negative 20 degrees. Right, that'll get me my direction vector. Since this is only two-dimensional, I don't have to worry about a lift or anything like that. Wonderful. Okay, so this will work out beautifully. And of course, we can find decimal components for all of these pieces if we so desire. It's not strictly necessary at this point. I mean, all they want is the part that's parallel to the plane, and this is the part that's parallel to the plane. Now you'll notice, let me just make a little quick note right here. I should do it in black. The magnitude of this must be equal to, because this is a unit vector, then when we take the square root, this part will all disappear. So the magnitude would be the square root of this piece squared, right? So if you distributed it, these two pieces would, by the Pythagorean theorem, make 1. So they're not going to do you any good. So the magnitude is going to be the square root of 100 sine of 20. Sorry, 20 degrees. That one's meant to be a degree symbol. It did not work out for me. Sorry, 20 degrees. There we go. Squared, which of course is just 100 sine of 20 degrees. That would be the magnitude of the parallel portion. Well, the perpendicular portion is going to work very similarly, right? So this is the answer right here. I mean, we found the parallel vector. It's right here. Or excuse me, the parallel component of the weight vector, right? So the shadow cast by the weight vector back onto that parallel vector. Now we're going to cast the shadow the other direction. So we're going to take the weight vector here and cast its shadow back onto the perpendicular vector. But of course it's going to work extremely similarly. So the weight for the perpendicular portion, the perpendicular portion of the weight vector, the perpendicular component of the weight vector, would be the length of the projection I better be clear on this. So this projection is of the weight vector onto the parallel portion, right? That's what you're doing. So you're taking the blue and you're casting its shadow back onto the parallel. This is going to be the length of the projection of the weight vector onto the perpendicular vector portion. And of course, going to multiply it by direction. All right, well, we already know this. This piece is y. And we found y to be 100 cosine of 20 degrees. So that part isn't going to change. It's still 100 cosine of 20 degrees. All right, then we just need its direction as well. Well, it's obviously going to be a unit vector, so it's cosine of something, sine of something. But now we have to go back and think about our axes. So when we did the parallel portion, here's our x-axis, here's our y-axis. The parallel portion is negative 20. But for the perpendicular, we need to start at the positive y-axis and swing all the way around to the perpendicular vector, the pink one over here. So that'd be 20, 70, which is 90, plus another 20. So that's negative 110. Negative because, of course, we're going clockwise. So our angle here would be negative 110 degrees. And there we have it. That is the component. I guess I could box these, because that was what was actually asked for. So up here, it was the 100 sine of 20 times all of this. And down here, it's that. And of course, if you want decimals, you may feel free to find decimals for each of these pieces and multiply it through, etc. Now you'll notice that the magnitude of this perpendicular portion would be 100 cosine theta, for the, or excuse me, 100 cosine of 20, for the same reason that it was 100 sine of 20 up above. So let me just make a little note of that. All right, now in order to keep this box in place, this block to stay in place, or slide down the inclined plane, depends on the relationship between the parallel and perpendicular weight vector components. So if there's too much weight in the direction that's parallel to the plane, which was the orange direction, it's going to start sliding down, right? So if it's too much in the parallel, it'll start moving down the block. Right? But how much is too much? That depends on one other factor known as the friction coefficient, mu. That's mu, mu in Greek, so mu. Rough materials like carpet or sandpaper will have a large coefficient of friction, right? Smooth materials like glass or ice will have a very small coefficient of friction. So suppose that the block will slide if the, or excuse me, this is not suppose, the block will definitely slide if the magnitude of your parallel vector is greater than mu times your perpendicular vector. Now suppose in our problem that mu was 0.65. Will our block slide? Okay, so this piece right here, the component in the parallel direction, that was x for us. So is x greater, question mark, we don't know, is it? So is x greater than mu, which is 0.65, times y, which was our the magnitude of our perpendicular vector. Okay, well, x, we happen to know, was 100 times the sine of 20 degrees. And then we don't know about this, so we're going to put question marks over it still because we're not sure. And then this is 0.65 times, and then the y was 100, the cosine of 20 degrees. So sticking these into a calculator or into Maple, whatever you like, this is 34.202. This part over here is 61.808. So it is in fact not greater than, which is good. Our block will not slide. Because the x is not greater than 0.65 times the y. All right, so how steeply could we make this, right? Still, notice, still with mu equal to 0.65. How much of an angle could we tilt it to? So in other words, instead of having an angle of 20 degrees, suppose we cranked the ramp up. Right? It'll eventually overcome the coefficient of friction and start sliding down. Right? So we want to know how large an angle can we go to. So that's what we're asking. How steeply can we incline? So what could theta go to? All right, well, it will slide, the block will slide if the parallel vector is greater than 0.65 times, well, sorry, the magnitude of the parallel vector is greater than 0.65 times the magnitude of the perpendicular vector. Okay, well, this was sort of like x for us. except we wouldn't have an angle. So we would say 100 times the sine, and instead of giving an angle, we would just say theta, right? Because that's what we're trying to solve for. And that'd be greater than 0.65, and then over here, this would be 100 times the cosine of theta. Like that. And so we want to solve this for theta. Well, the first thing I want to do is get the two thetas together. So this is no good to me. So I'm going to divide both sides by 100 cosine of theta. So that would get me 100 sine of theta over 100 cosine of theta. I think you can imagine where this is going. Well, obviously the hundreds cancel, so we don't need to worry about them. They divide away to 1, right? 100 divided by 100 is 1. And sine divided by cosine is the tangent. So I know that the tangent of theta has got to be greater than 0.65 because that's all that's left on that side. When I divide, right, here's what I'm doing. I'm dividing both sides by 100 cosine of theta, divide by 100 cosine of theta. These divide away, and it leaves me nothing but 0.65 over there. All right, so that would mean theta has to be greater than the arctangent, or the inverse tangent, of 0.65. So grabbing a calculator, that means the block will slide if theta is greater than 33.02 degrees. So how steeply can you incline the plane before the block will slide? Oh, okay. So we can incline the plane from theta equals 0 to up to and including, there we go, theta equals 33.02 degrees, and the block will not slide, which is the question they actually asked. In other words, the block will slide if it's greater than 33.02, so it will not slide if it's less than or equal to 33.02. Some slight paper issues over there, but you get the gist. Another way to put this is the block will not slide for theta, for 0 is less than or equal to theta, which is less than or equal to 33.02 degrees. That's another way to put it.